is operating kind of weirdly. Okay, so let's talk about tools of the trade. These are kind of the most common tools we're going to run into and some little basic notes about each of them. So when we're talking about analytical perspective here, gravimetric and volumetric wet chemical measurements require basic laboratory apparatus and manipulations. Technique's very important, and so is your equipment. Okay, knowing which piece of equipment to use is absolutely vital. Who here did the lab where they like graduated cylinder, measured things out in the balance, and used like different glassware to figure out like I'm measuring 10 milliliters and oh, that was 40% off with the beaker. And I'm measuring 10 milliliters again, and we take the volumetric flask, and now it's much closer. Anybody do that? It's usually that first lab measurements and called something like measuring measurements. No? Dang it. Okay. So if you were to ever like try to measure things out with a beaker, does anybody know how accurate that would be? It'd be about plus or minus 40% off. Okay? It's really, really, really bad. That's why you don't measure with a beaker, right? And so if you measure with a graduated cylinder, it's a little bit better, but not like amazing. Okay? If you measure with a balance, usually you can get really good actually, because usually they're less than 1% off. And so balances are pretty good. The analytical balance, much more expensive. We'll use that sometimes. That one's much more accurate. Okay. And much more, well, ours is much more precise. May not be more accurate because I need to calibrate that. But okay. And so you've seen most of these tools before now. We're just going to get this analytical mindset. Okay. So how can we use these to get analytical results, and we can do this in a safe and efficient manner? Now, does it make sense to just do every measurement maximum precision all the time? No. No, you're better off if you can get 10 measurements in the time it gives you to get one measurement the other way, and there's not a significant difference in your accuracy and precision. Why would you do the longer one? Because you're going to mess up eventually and you're going to get the wrong result completely, right? And so doing more times is actually much more important there, right? And so you got to keep that in mind. It's a conundrum that most of you have done it before in general chemistry and organic chemistry a lot. I see this a lot where people try to be super accurate for things that, realistically speaking, they're losing and having their measurements changed by 10-20% anyways. And so if you're trying to be super accurate on an analytical balance and spend half an hour doing that, it absolutely makes no difference, right? You're just wasting that time. Okay? So you have to, being analytical doesn't mean just maxing out your precision every single step. It means knowing where to cut precision and what is meaningful precisions. Okay? If you're adding something in excess, does it matter how much you add? Not really. Like you just need to add it more than you need. So do you have to weigh it out super accurately? No. Does it matter how accurate the label is? No. If you're adding 3 times versus 4 times, it's not going to make a difference. Okay, so this is kind of like optimist, half full. Pessimist would see this half empty. Realist would be 26 milliliters of liquid. And analyst, what is this unlabeled beaker? A little fun factoid is there actually are unitless numbers that you can use. And if you guys ever want to talk about it, you can define all units by like galactic universal constants. And they all boil down to 3 constants that you can do everything by. And so you don't need units. Yeah. I really kind of wish they'd do it, but then numbers would be very strange. So, yeah, like everyday numbers would be 10 to the negative 30. Or 10 to the 30th. Either way. Now, Safety in the laboratory. Primary safety rule: evaluate the hazards, then avoid what you or your supervisor deem to be dangerous. Hopefully, both of you agree on that. If you both don't agree, you should probably talk. Okay. But notice what the most important thing for lab safety is: knowing what you're working with, right? You can never be safe in a lab without knowing what you're working with. Okay. Okay. Does anybody have any questions about any of these lab safety things? I think I cover them pretty well in the safety module. Anybody confused about any of that? I'm not going to require it, but honestly speaking, I probably should in the future. If you guys want to wear a lab coat, it's actually would be recommended, just because then you don't spill on your clothing and stuff. Most of you are wearing nice enough clothing that you probably don't want to like dissolve it. So if you're going to go to a meeting after this, by the way, seriously wear a lab coat or something, because the number of people have been like, I'm doing an interview after this, and then $400 suit. And then I'm like, no, don't do that. And they're like, I'll be okay. Never spilled on myself before. I've had 3 people do that. Like, when you have nice stuff on, that's when it's going to happen. Okay. Personal protective equipment, by the way, is abbreviated PPE, in case you're ever wondering. So if you ever hear PPE, that's what that means. It means things like your splash goggles. We have to wear splash goggles in this lab very specifically, because I'm using fairly caustic materials, because we got to break everything down all the time, right? And so if anybody splashes to the side of you and gets you, they're going to hurt you. Okay. Now, having said that, technically, you could probably get away with those little shields they give you at the deal, but I would prefer not. Okay. They don't work quite as well as actual splash goggles, right? Yeah. They're like 90% there, but they're not. Yeah. Also, those green and clear ones, they are not actually splash goggles, but they're, again, like 90% the way there. But they have a gap right here, meaning if somebody actually does splash you in the face with something, it's going in on your eyes. Okay. Okay. Does anybody have any questions about any of this? If we're using a lot of organic solvents, we'll want to use the fume hoods. We do have an overall fume fan in there, and so that will do like 80% what a fume hood would. But if we start building up a smell, we really need to start moving over to the fume hoods. Okay. Spills are actually one of those things that are kind of dangerous. You want to immediately clean them up, but only if you know what they are and how to be safe with them. Okay. If you don't know and you're not sure, then you really need to ask somebody for help. Okay. Most of the things we spill here will be fine if you just go ahead and neutralize it and then clean it up with soap and water. Okay. Most things actually you can just clean up with soap and water, like dilute acids. But there is so many examples of unsafe lab procedures. Did I ever tell you guys about the graduate students at California that killed themselves? Okay. Have I ever told you about selenium labs? Yeah, so there's certain compounds that burn whenever they're contact with air. So whenever you contact them with air, they'll just light up and start burning. And so they actually make these labs. You've probably seen them before. They have like little quickly done buildings, kind of like those buildings they take in the back of trucks and just drop off on place. And they have all these equipment plugged into these holes in the side. And what you'll see is like 5 of them in a row. And you'll have like a burned one, one that's in use, and then you'll have a bunch that are like just empty with none of the equipment in them, or maybe starting to put the equipment in. Okay. And it's literally because they light them on fire so often that they just make them disposable and you run away if something happens. Yep. Gloves are not invincible. Neither is your skin. So anybody ever heard of DMSO? Yeah? Okay. Often used in those patches that absorb through your skin. A fairly common solvent as well. And so there are chemicals and drugs that will absorb through your skin. There's ones that will absorb through the gloves through your skin into your bloodstream. And so gloves are not 100% protection, okay? Especially when you're working with organics, gloves have a tendency to just like pop around you because the fumes actually start dissolving it, right? That's why in organic chemistry, you usually don't use gloves because they don't help. All right. Anybody have any questions there? Okay. Now, clean, uncluttered labs, very important for having a lab that is less prone to mistakes. Okay. If you don't have things all over the place, it's less likely you're going to cause issues, cause mistakes. All right. How about labels and safety data sheets? Anybody know where the safety data sheets are? It is. Yeah. Those are those folders. They actually say MSDS here because they changed MSDS like 10, 20 years ago to SDS. They just haven't changed the signs up on the floor yet. I guess I'll probably be doing that sometime in the near future-ish when I get a chance. Probably this summer if they have air conditioning. Because I just can't do it at like 100 degrees. It's too much. Okay, labeling is going to be something we're constantly going to be fighting over, and we're going to have issues with us. You guys are going to make batches of chemicals, and you're going to need those to like do dilutions and stuff. And then what should you always do every single time? They need to be labeled. Okay? If they're not labeled, what's going to happen to them? They're going to get dumped into waste. Okay? And they might have to be treated as very dangerous chemicals because I won't know what it is. Right? Okay, so unlabeled bottles that are forgotten in cabinets, refrigerators, these actually can become incredibly expensive disposal issues. I once saw somebody not know what a gallon of something is, and it cost them $20,000 to dispose of it. And so everything should always be labeled, right? Okay. Anybody know what a label actually has on it? First off, how do you do a label? If it's glass, let's say the container's glass. Okay, so tape and a Sharpie works okay as long as you can tape all the way around so it can secure itself. You can actually just straight up do Sharpie on the glass if you want because you can see it on the glass as long as the liquid within it is not going to be dark colored. Okay. Make sure your glass has any previous labeling rubbed off. Anybody know how to rub labeling off if it's written directly on the glass? Alcohol. Yeah. You can use acetone too. That's kind of expensive and unnecessary. Yeah. But alcohol is usually all throughout the lab. The isopropyl 70% works fine. But ethanol, methanol, those all work too. And it's cheaper and usually less hazardous around the lab. Okay. What else do you need? What do you need for your label? What are the components of a good label? Huh? When it's made. Very good. The name of what? Yeah, the compound solution. If it's a solution, make sure that you indicate it's like this percentage or this molarity or what it's in if you made it not using water. Okay, and what else should you have on it? Okay, we have the date is made, what it is inside of it. The last one is who's responsible for it. If you need more information about it, who can I talk to? Okay. You'll see that like even the distilled water has date I made it and then my initials on it. Okay. Because I end up stopping the distilled water all the time because I'm always in that lab apparently. And sometimes I don't. We have biblical floods. um, so, like all the bottles have my name on them, you might notice. I wonder why. So, anyways, always put your name on it if you're the one that makes that label, okay? If you update that chemical for whatever reason, like add something new to it, add a new date that's when you changed it, and add the new conditions. Okay? Anybody have any questions about that? All right. If we find any bottles that don't have all this information on it, what's going to happen? Yep, it is going to go in the waste. Yeah. And I'm going to have to do some treatments on it. So if you're lucky, I'll have it sitting in the waste compartment, not yet poured out. Okay? Okay, now, what sort of bottles do you use? Can I use glass? Nice volumetric flask. Yeah, you can use a volumetric flask. I wouldn't recommend leaving it that way because you don't have that many, but like actually in most labs they have plenty and they just do. Yeah. Is glass always the answer though? I made up sodium hydroxide. Should I leave it in glass? Anybody know what sodium hydroxide does glass? It reacts with it. It actually dissolves the glass. Or HF, hydrofluoric acid, also dissolves glass. Okay? And so leaving it in glass is probably not a great idea, is it? Yeah. In fact, has anybody seen the syringes that are fused together? Those are almost always because the sodium hydroxide was left in it. They like rinsed it and they put it back but didn't get all of it out. And so KOH or sodium hydroxide dissolved the glass, it dried out, and the glass is actually fused. Okay. Anyways, so it isn't always like automatically anything can be stored in this. Okay. You have to know what you're working with, right? But in general, you need something that can protect it from the atmosphere and perhaps light, if light's important. Okay. That's where the amber bottles come in, by the way. They protect it against light. Right? You can also wrap it in tinfoil to protect it against light. That's why the bottles that we use for plastics are very thick, is they keep the atmosphere out. Did anybody know that atmosphere can actually dissolve through water bottles? Yes. Yeah. So if you were to look at like that bottle right there, that one would actually allow atmosphere through it. Now, your bottle would be more resistant to it because it's thicker. Okay, but they're the same materials. It's just more resistant to it. Eventually, it will allow some atmosphere exchange. Okay. Safety data sheets. Everybody knows where to find those now. Everybody knows how to use them. Okay. Fantastic. This right here is the GHS hazard pictograms right here. This tells you how it's hazardous to you. Hopefully you'll have all those notes in your lab notebook as well. So you don't have to just be like, I have memorized this. The low categories 1 or A are the most hazardous on this scale. Okay. Please note that when we're talking about hazardous, there are certain things that have not been tested. And so they've actually labeled them based on other stuff that's kind of like them. And there are different levels of danger. Mm-hmm.
So that low category thing, if it's like, I'm looking at a lot of safety issues. If it's like respiratory irritant category 3, that's not as bad as a category 1.
No. And this GHS, be careful though, There's a whole nother hazard system. Yeah. With the blue, yellow, red. So do be careful that you actually look up if they're not directly these symbols here. Okay. Because there's actually 3 systems in use. Yeah. And that system, the blue, red, yellow, that's actually the reverse. It's so there's different systems. Just beware. Yeah.
These guys right here. So this is that. It's the OSHA.
Which one is this?
Oh, I just pulled up a random. I think it's hydrochloric acid or something.
Okay. The reason I'm asking is I can tell by what it is,
Okay.
which direction it is.
Oh.
Yeah. So, yeah, this must be GHS. Yeah.
Okay.
Yeah.
Okay.
Because see how it's corrosive, highly corrosive, target organs, respiratory system.
Mm-hmm. Yeah. Okay.
My guess would be that's GHS, but you'd want to actually look. It should define it somewhere in there if you read it through. Okay. Everybody did the green chemistry modules. Okay. Let's try not to pollute so much. Yeah. Okay, so did everybody see the lab notebook materials? And I went over that in lab, okay? Nobody has any questions about that? Okay, I'm going to kind of skip through. Okay, so this right here is the analytical balance. I have to warn you, number one, be really careful with our analytical balance. We only have the one, and they're a significant investment of money that we can't just do willy-nilly, okay? I do need to recalibrate it because it has been moved a few times. What it does is it uses electromagnetic force to compensate for the load that's placed on our pan. What does that mean about loads you can place on pans? Okay. Let's say that you did it on a force, you're resisting the force on a load, and I try to weigh an elephant with you. You going to be able to resist the force on that load? No. And so there is cutoffs on here. Every analytical balance has a maximum weight they can weigh. Okay. The other thing that happens with analytical balances is that they have a percent and usually banded percentages. So if you weigh something that's a lot of mass, you're going to have a less precise measurement. Okay. At least an absolute measurement. Instead of being like 1 microgram off, you might be like a milligram off. Okay. Okay. So if you can, try to reduce the amount of mass, absolute mass you're measuring. Okay. But only to a point. Because once you get down to a point, you're going to have effects that are from the it's so low, I have errors, right? Okay. Typically, you want to stay in like the 10 gram range. And that's why like 25 grams is what we were shooting at for that problem. You don't want to be in the hundreds. You definitely don't want to be in the kilogram. You probably won't be able to measure that. And you really don't want to get below 0.1 usually. Once you're below 0.1, you also start having problems again. Okay. Now, to weigh it, you need to place a dry vessel. You tear off the mass of that vessel. It needs to be in the middle of the pan. Can it be hot or cold? What happens if I heat the pan? What happens to the air under something I heat? Pushes up against it, doesn't it? Okay. If I cool the pan, what happens? Pulls it down. Okay. So you have to be careful. It needs to be essentially room temperature, and you need to be really careful about it. So the top loading or precision balance typically has a readability of about 10 to 100 milligrams. and can afford convenient weighings when high precision is not required. A microbalance, on the other hand, will measure milligram quantities with about a 1 microgram difference. Okay. And these are much more expensive, and that's typically what's called an analytical balance, to separate from these right here, which is the top loading or precision balance. Okay. The precision balances are the ones you've mostly used. Readability, the smallest increment of mass that can be indicated, is typically going to be displayed right here. Okay. You notice this one looks a lot like the organic balances right there. This is what we should have in the organic lab. We do not. Whenever I need to replace those, I'll get to these. How to weigh a chemical again. Clean dry vessel right. Tear off that vessel. Put what you need into that vessel. If you're using this right here, the analytical balance, you need to take the vessel off. But typically you want to do it in such a way you're not going to be adding something to it. Okay? For example, if you're not wearing gloves, what would happen if you touch it? What happens to anything you touch? Oil, right? Your fingerprints get left. Okay? If you're using an analytical balance, then your fingerprints are going to be weighable. Right? They're actually going to affect that. You will see it. Okay. Whenever you're taking a measurement, including the tearing measurement, you need to close the windows, make sure the little bubble is lined up and nobody's moved it. Okay. And why would you need to close these windows? What would happen if you blow on this? You exhale during this measurement. It's going to read, right? It's going to read well over the microgram quantities. In fact, it'll read a milligram-ish quantities. So like a 1 milligram quantity. That would be a breath. So you'll actually read yourself again. I know. Okay, so you have it teared, you have your vessel, you weigh stuff out into your vessel, you put it back on, close the windows, get the weight, right? Everybody good with that so far? Okay. Never, ever, ever do you place chemicals directly on the weighing pan. You do not spill chemicals on that mechanism. That's why you always measure everything off of the balance, right? At least for an analytical balance. Okay. Now, these ones right here, these top loading or precision balances, fine. Weigh on, you can put stuff on them, that's okay. You can just put your beaker on there, you can tear it off, and then you can just very carefully measure stuff out directly out into the beaker. If you spill things on it, you just clean it right then and there. You may have to redo your tearing and all that. There is a trick if you want to play it. What you do is you put a weighing boat or weighing paper below what you're weighing, tear that, and then if you spill stuff, you just take that weighing boat or weighing paper and empty it in, and then put it back down. Okay? The accuracy won't be greatly affected. Okay, what about hydroscopic reagents? Anybody know what hydroscopic reagents are? Okay. So this is where your reagent absorbs moisture from the air. Major problem in Tennessee, obviously, right? Like, not so much of a problem out in the Rockies. Huge problem here. Okay? And what you'll see is you'll see this a lot with things like, well, really, kind of most things are some degree of hydroscopic. It's pretty rare to have zero hydroscopic for solid salts that are not already completely hydrated, which is a lot of the stuff we'll use. But the ones you really, really see is a lot. Has anybody ever saw solid like potassium hydroxide or sodium hydroxide? No? I know we don't give it to you a lot because you tend to take too long and then you can't, it absorbs all the moisture. So we just make up like 50% solutions for you and give that to you. But so if you take solid sodium hydroxide and you were to just put it in a weighing boat and then go clean something, come back, what you would see is it would actually have droplets of water on it. Okay, and it would partially solvate. Some of it would actually dissolve, right? And that's because it's actually quite hygroscopic. Is it the most hygroscopic thing? No, there's more hygroscopic stuff. That is even worse. Okay, so this will rapidly absorb moisture from the air. When you're weighing, a capped bottle will contain that dry reagent and keep the water from going in. Does it perfectly keep all the water out? No. So remember, whenever you're capping things, you have a headspace, right? So every time you uncap it, you're going to add that amount of moisture in. Okay? So you got to be really careful with these things. You'll then take that reagent, you'll quickly pour it into your weighing bottle, into a receiver. You'll cap the weighing bottle, weigh it again. That difference in the mass of the reagent delivered from the weighing bottle. And that's why you do the difference in weights, is because it helps you avoid that issue where you're hygroscopically picking it up as you're trying to read it. Okay? Okay. Does anybody have any questions so far? Okay, if you're using an electronic balance, you actually want to set the initial mass of your weighing bottle to 0, and then you deliver reagent from the bottle, and then you reweigh the bottle. That actually is a faster way to do this. Okay. That way you can just do a negative reading, and that's your reading of the stuff you delivered, right? Okay. It's not going to be perfect. You'll still have a little error, but it'll only be the headspace and moisture area rather than all the moisture. Okay. There's actually a second way of doing this, by the way, that's a little tricky. If you have a hygroscopic reagent and it's been sitting out and it's fully dissolved, then that's your KSP. You can actually figure out the equilibrium concentration and use equilibrium concentrations, your solubilities. Okay? But it's not as accurate as having it completely dry and using a balance. That's a better way. Okay? But it's a backup way in case something goes wrong. This is actually how an electronic balance works. You'll notice that it's actually a lot more complicated than you probably thought, right? In that little electronic balance that they're selling for $200, there is all of this. Okay? Okay, so this actually is the internal calibration mass. This mass does get affected by various things like temperatures, etc., and your lab conditions. Here you have a balanced pan. This is the load receptor. So what we have here is we actually have a firm anchor with parallel guides. This one is actually going to be changed depending on what you put on it. And this one is the one that actually affects your sensor over here. Okay, I'm not going to go into any more detail about the electronics here, unless you really want. But that is actually a diagram of a balance. Okay, if you ever want to actually, like, if this becomes important for some reason, right there. Right? Your book does a very good job of taking the overall diagrams of these instruments. Now remember, this is like a overall diagram, right? So for example, there's a microprocessor in there, CPU, that does these calculations. Okay? And converting them into fairly understandable things. Okay. So if you ever have something go terribly wrong and you need to figure that out, there you go. Okay. Now, when we're measuring mass of something in a gravity well like Earth, what are we actually measuring? Can you measure absolute mass? No, you're measuring the weight, mass times gravity. Okay. And so what you're actually doing whenever you're using a balance is you're actually measuring weight. And that's why you typically call it weighing things, because you actually are weighing. It's only if you were without gravity in space that you could actually measure mass, though even there it'd be arguable if you can do it. Okay? It's not that simple. The other thing that's happening here is the magnetic field around you is affecting these measurements. Okay? California is actually quite famous for having places where they would have the same gravity, but they actually have magnetic fields interrupting. And you have to actually have to like recalibrate them going from lab to lab. Anyways, this is an electrostatic process. It's that current changing based on this weight. That's actually what we're measuring. Okay. Okay, so let's talk about some weighing errors. Typically, to minimize vibrations, you're going to place analytical balances on a heavy table. Usually, it's a marble slab is actually the best way to do this. This is actually a major problem that's developed from having new labs. Like back in the day, they used stone for everything. That was like the top tier deals. Sometimes it was asbestos, so which worked really good until somebody fractured it. Then you breathed it in. Not so great. Though I guess if you're wearing masks, not such a big deal, anyways. Anyways, so they went to lighter materials like plastics, and so balances have actually started working as well because they just have lighter material plastic tables, right? You level the balance using adjustable feet. There's a little bubble meter. Has everybody seen a torpedo balance? Same looking thing. It's just a little circle with a bubble. If it's not level, what's going to happen? Will gravity be pulling straight down then? No, gravity will not be pulling straight down. You will get mismeasurements. Needs to be close to the center of pan. If you're off center with your weight, not volume, weight needs to be close to the center of the pan, okay? If you're off center with your weight, again, it's going to not fully transfer that weight to the bottom. Ambient temperature has to not have active currents. If you are drying something in the oven or heating them up, what do you have to do? Wait. You have to wait. You cannot do them right away. You're going to cool the samples in the desiccator. We do have one desiccator currently. We're going to try to find some of the other desiccators, but I've been told they may have been given away as and been used as dishes. So that's sad. Now, fingerprints can affect the mass. Anything that comes off of you can affect the mass. Keep that in mind. It's actually very common to shed skin particles, oils, etc. onto things and affect the mass. Magnetic materials should be weighed on a spacer so they don't pull the parts of the balance on. Modern balance have built-in calibration capabilities, and you should recalibrate a modern balance every so often. Usually it's something along the lines of every month or so in a professional lab. Right here, these are different denominations and different tolerances depending on the class of your balance right here. Okay. These tables are one of the most useful things in the book, by the way, if you go out into your career. Okay. Because there's not a lot of places that's actually like collected. And people lose the damn manuals all the time. So, or sometimes they just don't have them on them, like our calibration weight, which is bizarre. Let's talk about some balance troubleshooting. Erratic readings. The balance door is open, object hot or cold, static charge on the object. These can all make a difference. Okay? Static charge can actually be more common than you think. This can be dissipated by patting the balance and the object with an anti-static brush or anti-static gun. Anybody know how you can fix it if you don't have those things? Copper wire. Just take a copper wire, put it to a large sink, and then touch it. Okay. Reading drifts downwards as you're weighing. Probably a liquid evaporating. That's one of the most common things. If your reading drifts up, you're typically going to be absorbing moisture from the air, and so you're weighing higher and higher numbers all the time. Buoyancy, this is going to be an upward force that's exerted on an object in a liquid or gaseous fluid. This is the buoyancy equation right here. It's the same buoyancy equation for like a boat, okay? Or anything floating, like a balloon in air. So the object weighed in air appears lighter than its actual mass by an amount equal to the mass of the air it displaces. True mass is actually the mass measured in a vacuum. Standard mass in a balance is also affected by buoyancy. It weighs less in a air than a vacuum. Buoyancy error occurs when the density of an object being weighed is not equal to the density of the standard mass. So there's actually a bunch of really cool examples that can be worked through in here. For example, if I was to take a ping pong ball and I was to push it down into a flask with water, it would actually have the same mass as its area in water. Okay? Despite the ping pong ball is way less mass. And that's because the force I'm exerting. Okay? On the other hand, if you were to like suspend an iron ball within a flask, that would again have the same mass as the water. Okay? Because I'm suspending it. It only has a portion of that mass that's being applying pressure. Okay? And so again, this is the buoyancy equation. It's how you can figure these things out. Okay. The same sort of thing happens if you try to weigh stuff that can float. For example, weighing like CO2 in a bag is a really hard experiment, actually, because I tried it once with a class. It did not work well because the bag wants to float a little, right? And so your buoyancy ends up killing the measurements, even more than you'd think. This is a buoyancy correction. So the apparent mass measured in air is multiplied by the buoyancy correction to find the true mass. Okay. And so when you weigh water with a density of 1 gram per milliliter, the true mass is actually 1.0011 gram when the balance reads 1 gram. And so this is actually the error from the buoyancy right here. Okay. For NaCl with a density of 2.16 grams per milliliter, the error is this right here, 0.04%. Notice as you get more dense, this buoyancy error fades off really fast. Okay. So for example, as we get up here, density 4.45 grams per milliliter, we only have an error of 0.01%, right? Does this ever go to zero? No, not really. It kind of flatlines pretty close to zero, but usually doesn't actually hit zero here. But okay, this is the buoyancy corrections. So we have tris using its primary standard for measuring concentration of acids. Volume of the acid reacts with the known mass of tris, tells its concentration. We're going to find the true mass of this tris sample. So we have 1.33 grams per milliliter. That's the density. If we weigh it out and it says 100 grams, 100.00 grams, what would be the true mass? So we're going to take that buoyancy formula. We have 100 grams. This right here is 1 minus, and then we're going to use the density of the air. Note that we'll use book values for the density of air because we don't really have a way of measuring it, but you can actually have devices to measure density of air, okay, in a lab. And it does change a bit, okay, depending on if your sea level, moisture in the air, etc. This is that grams per milliliter. That's having to do with this number up here, right there. Okay. And that's the weighing standard within the balance is 8 grams per milliliter density. This right here is, again, the air, and this is versus our sample. And that's the term on the bottom. Okay? If you ever forget which is which, by the way, this one here, the lighter it is, the larger this number, right? Okay? Okay, so we go ahead and do that sample. Again, we have the mass here that's multiplying. And so what we get is we get 100.08 grams. Notice that we have a 0.08 gram buoyancy difference, right? From our mass of our tris. Okay. And so that is a percent difference of 0.08%. And if we did this with that same measurement, well, we'd have an error of 0.08% in our final molarity, wouldn't we? Okay. Anybody have any questions about that so far? Mm-hmm. Air and the counterbalance. It's the actual like balance.
Okay.
Yeah, this would be a number that would correspond to your balance. And the formula is right up here, though it's in your book as well. All the formulas are in your books, by the way. Next time we'll do burets, I guess, because I ran out of time. And I'm going to try to cover that really fast. So we are on chapter 3 and 4 then. Okay. Does anybody have any questions? Did I lose anybody? Huh? Everybody alive? Kind of?
Are all the chapter 3 due date stuff going to be shifted back?
When was the due date?
I believe yesterday.
Yeah, we'll shift chapter 3 back a bit. Okay, what I would like to see though is can everybody try chapter 2 stuff and see if you actually have any issues? Okay, if we don't have any issues, I might just go ahead and let my video on chapter 2 stand and just move on to chapter 3 so we can spend more time on new material. Okay?
I can't speak for the
Huh?
other people. We mostly finished chapter 2.
Okay.
Most of us. So.
Okay, fantastic. Yeah, it's pretty like it's not a lot of stuff that's you get stopped on. Yeah, you pretty much.
Besides like the Google Excel or whatever, that was just out of nowhere.
You liked that? Excel is useful. Learn Excel.